So we're ready now. We're left with just our square planar and tetrahedral d orbital splitting diagrams. And now we can figure out, how do we use that weird data that I collected on the NMR spectrometer somehow to tell me how many unpaired electrons I have in my complex, right? Remember for this example, we had a D6 metal complex. We called it iron 2. Honestly, any D6 complex will follow the same analysis. Change the number of d electrons, you'll change the number of electrons in your splitting diagrams. You might need to count again how many unpaired electrons you have, but you'll eventually get it. All right, so if you look into some of the resources I gave you on the Canvas site, you'll find a paper in which all of the math here is worked out. I'm going to skip the derivation for now and just give you the equation. We'll start by applying the method, and then if you're interested in how the method came about, I'll post another resource on Canvas for you to check out the derivation of that. So here is the commonly published equation that you might see for magnetic molar susceptibility. Chi m is our term, and you might see a small m here. Sometimes it's mass, sometimes it's molar, so you need to double check. I'm going to be specific so we don't get confused. So the molar susceptibility, chi m, equals the absolute value of -3 delta F divided by 4 pi times F times m times a conversion factor of 1,000 centimeters cubed per 1 liter, converting from our concentration units that we are going to put in to our data and out, times m prime divided by n. All right, all that closed bracket. If we simplify that down, we get 477 divided by essentially 2 times delta F over F times C. And here, C is our molar concentration. F on the bottom is our magnet frequency. In this case, we have a 400 megahertz or 400 million hertz spectrometer. Delta F is the difference in frequency of the two peaks that you measured of the Evans method spectra. So if you have your TMS peak right there at 0, there should be a second little shoulder peak next to it, and wherever that shoulder is, the difference in frequencies between those two gives you your delta F. And that should be in the same units as F, and usually hertz is the one we'll use. So you have to convert megahertz to hertz and also get the difference in frequency in hertz. It will not work if you use the difference in frequency in parts per million, although there might be a way to do that. If you're clever with your units, I'll let you figure that out on your own. Okay, just double checking the molar concentration, in other words, is the number of moles per volume. We can see that worked out here where we have our conversion factor. M prime is the mass of your sample. N is the number of moles of sample. In other words, that's your molar mass. Little m down here is the mass concentration. That's got units of grams per milliliter. That's directly from your data. And then this term here will be your molecular weight. Molar mass, however you say that. And that gives you pretty much what you need. So if you're confused on what molar concentration is, going back to the bigger form of the equation is easier. So m prime is the mass. N is the number of moles. Little n is the mass concentration. In other words, the grams per milliliter of your sample. F and delta F are the same. You all know pi. There you get it. So once you've done this, that gives you this value of chi, the molar susceptibility. And we can take the molar susceptibility value and can convert that into a relationship with a number of unpaired electrons.